Okay, this is the second hour of Physics 1B for December 6th. We just started talking about sound waves, and we're going to do a couple of these problems here. First, we're going to do this one, amplitude of sound wave in air, and then one about the inner ear. Okay, so it says, in a sinusoidal sound wave of moderate loudness, we haven't really talked about loudness yet. In a second we will, though. The maximum pressure variations are about 3 times 10 to the negative 2 pascals above and below atmospheric pressure. Find the corresponding maximum displacement if the frequency is 1000 hertz. In air, at normal atmospheric pressure and density, the speed of sound is 344 meters per second, and the bulk modulus is 1.4 times 10 to the 5 pascals. So we've got bulk modulus. Notice that this number is 5 orders of magnitude lower than the bulk modulus for things like steel. Just to pull them back up here on this. Where was it? Here we go. If you look at these bulk moduli for things like steel, they're all in the order of like 10 to the 10. Even rubber is, what is that? 10 to the negative, 10 to the 7. So as you can see, air is much more flexible at 10 to the 5 pascals. Okay. What else do we have? We're given velocity of 344. We're given the frequency of 1000 hertz. And we're also told that the maximum pressure variations are about 3 times 10 to the negative 2 pascals above and below atmospheric pressure. So that's going to be our pressure maximum is 3 times 10 to the negative 2 pascals. That's a very small change, right? Apparently, your ear can apparently sense very, very tiny fluctuations of pressure. And that's all the information we're given. What are we finding? Find the corresponding maximum displacement. So I think that is A in our equation, where our equation said that pressure max was equal to, I think it was like kBA, right? Let's go back up just a second. Yeah, bulk modulus times the wave number times the amplitude. So we're going to have to figure out the wave number, but we're given the rest of it. And we're looking for the amplitude A, which is going to basically just be the maximum distance. So what does this mean? This is going to be what is the maximum distance that air molecules move, basically, right? So we've got a sound wave. What in the hell just happened there? That was weird. Oh, okay. So we're imagining that there's some kind of a sound wave, right, that's being produced by maybe something that's moving back and forth, and there's going to be these pressure fluctuations that we were talking about. But A here is, if I look at a single molecule, that molecule is going to be vibrating back and forth. It's also going to be zipping around throughout the room. And A is going to be, half of that total displacement, right? So this is A and this is A. You could say that the total displacement, I guess, is 2A. Anyway, we're trying to figure out how much are the molecules actually moving. That's what this question is. Okay, first of all, we need to find wave number K. So wave number K is equal to 2 pi divided by lambda. We don't know what lambda is, but we can find it because we're given velocity and frequency. So we can say lambda is going to be equal to velocity divided by frequency. So K then is equal to 2 pi f over v, it looks like. Frequency divided by velocity will give us this is going to be radians per meter, which is what we want. If we plug that back into our equation here, we get that maximum pressure is equal to 2 pi f over v times the bulk modulus times the amplitude that we're trying to solve for. Rearranging, we get P max v over 2 pi f, and then divided by b should be equal to the amplitude A. I guess these units are going to work out. Well, this is pressure over bulk modulus has units of pressure as well, so these two, the units will cancel. So we just have, it should work out. So we get pressure max was 3 times 10 to the negative 2 pascals multiplied by velocity So let's see if this equation makes sense. Can you all calculate this for me and tell me what you get? And I just want to like talk about the equation. What do you get out of this one? (1.16 times 10 to the negative 8). Very, very tiny number. Oh, we had different answers. Maybe somebody else want to kind of verify? Because it looks like 10 to the negative 8 is, everyone's agreeing on that. That seems reasonable because you got -2, -5, -3. That makes sense. Okay, the first answer looks like it's probably correct. That is a very tiny displacement, right? I mean, we have to acknowledge that that is, what is it, 0.12 nanometers. These molecules are not moving very far. Now, I don't know how realistic all the numbers that we're given are here. We have to just kind of take them for what they are. But what we can do is we can look at the amplitude of motion, that is to say how much these particles are actually moving around in the air. And we can see if it makes any sense. So the first thing I notice is that the amplitude would be bigger if the maximum pressure variations were larger. That seems reasonable, right? Because if the change in pressure is huge, then the particles are going to have to be moving long distances. We multiply by this. Let's come back to that. But in the denominator, we have the bulk modulus here, right? So if we compare the amplitude of this sound wave passing through air compared to the amplitude of the sound wave passing through something like steel, if this was steel, then the number down here at the bottom would be like 10 to the 10 pascals, and our answer would be 10 to the negative 13. That means that in steel, the molecules would be vibrating at much smaller amplitudes. That seems reasonable, right? Because air is flexible and things can move around very easily, whereas steel is kind of this rock-solid thing where, yeah, the molecules can vibrate a little bit, but they're not going to vibrate as much as air molecules do. And of course, that's going to affect the sound of a sound wave in steel in terms of how you hear it compared to a sound of a sound wave in air. So there we go. Anyone have any questions before we do this next problem? A. It's A. Just saying 2A is the total distance from here to here, but this is just A. This is equal to A. Okay. So let's do this next one. Move these down a little bit. Okay. I put this picture here because I think we need it. Oh man, I know nothing about anatomy. I'm so bad at it. But this is supposedly the inner ear, where you've got something called the cochlea, ossicles, the malleus, which is sometimes called the anvil, the incus, the hammer, and the stapes, which are the stirrup. And they're all just like pointing to these orange globs here. I don't know what I'm supposed to make out of that. Anyway, here's the problem. It says a sound wave that enters the human ear sets the eardrum. So where's the drum? Oh, right here. There's the drum. Then here's the auditory canal. So this is the outside ear. This is the part that comes into your ear, and here's the drum. This is the part that does the vibrating that we then interpret via this mechanism of whatever's going on inside of here. Okay, so it says a sound wave that enters the human ear sets the eardrum into oscillation, which in turn causes oscillation of the ossicles. What a great name. So the ossicles are all of these bones. The malleus, the incus, and the stapes. Okay. It causes this oscillation of the ossicles, a chain of 3 tiny bones in the middle ear. Oh, these are bones. That's interesting. This bone, these are bones? Okay. The ossicles transmit this oscillation to the fluid, mostly water, in the inner ear. There, the fluid motion disturbs hair cells that send nerve impulses to the brain with information about the sound. That's pretty cool. The area of the moving part of the eardrum is about 43 millimeters squared. So this is the area of the eardrum. So let's call it the area of the drum is 43 millimeters squared. And that of the stapes, the smallest of the ossicles where it connects to the inner ear, is about 3.2 millimeters. So the area of the stapes, which is the stirrup. Okay, so this is the outer area, but this area here is much skinnier. It's 3.2 millimeters squared. For the sound in example 16.1, the one that we just did, determine A, the pressure amplitude, and B, so A, we wanted to find the pressure amplitude, and in B, we want to find the displacement amplitude, which is A, of the wave in the fluid of the inner ear, in which the speed of sound is 1,500 meters per second. So in this case, the speed is going to be 1,500 because we're now on a fluid. Okay, the pressure amplitude and the displacement amplitude of the wave in the fluid of the inner ear. So these both go to that, in which the speed of sound is this. Okay, so what are we going to do to solve this one? Feels like we've got these two different areas here. We've got a velocity. I don't know why. I start to think about the continuity equation, but maybe that's bad. To find the pressure amplitude. So in the previous problem, we were given the pressure amplitude. That's this P max. Oops, sorry. That's P max. But we know that pressure amplitude is equal to this. And we're going to have a wavelength. This is amplitude, not area. This is bulk modulus. We can find the bulk modulus of water because it said it's mostly water, and then wave number. So we actually need the information from this problem. So I think I might copy this and then paste it down here. So we have all the data about the wave, or paste it like over here somewhere so we can still see it. And what else do we know? So we have why would the pressure amplitude change? I guess is the first thing that I'm thinking about. We were given that this was the pressure amplitude before, the amount by which the pressure changed. And we have this equation that pressure max is kBA. This is amplitude, not area. Why would the pressure change? What do you all think? Is the pressure amplitude just the same? Probably not, because it's water now, right? It says mostly water. It says fluid motion disturbs the hair cells. The area of the moving part is this. That of the stapes is this. For the sound, determine the pressure amplitude. Okay, so I don't know. What do y'all think we should do? What do you all think? Just writing down all the equations that we have. How do we get started here? We have a new sound, or a new velocity, right? So that's obviously going to affect K. I'm pretty sure the frequency has to be unchanged. Because if the frequency coming in is 1,000 hertz, then the frequency going into the inner ear canal also has to be 1,000 hertz. Otherwise, you'd have this kind of buildup of energy occurring. The wavelength can change, but the frequency can't change. I don't know how you're supposed to know that, but I know it. We're going to have the same frequency. So I'm pretty sure we can find a new K, right? So let's start off by doing that. We'll call this K water. And that's going to be 2 pi times 1,000 divided by our new velocity. And let's calculate what that is. So keep in mind what I just said. Frequency isn't going to change. Whether you're going from one medium to another medium, your frequency is always going to be the same. Something to keep in mind for the problems you're going to see in this chapter, because they're probably going to assume that you know that. I don't know how you're supposed to know that other than me telling you, and I can actually prove to you why it's the case if you want. But just something to keep in mind. So I get 4.19. The units for this are radians over meters. So we've got a new K. We're also going to need to know what the new bulk modulus is, right? And we're also going to need to know what this is. So we can look up bulk modulus, but this is the thing that we're not going to know immediately. And to find the maximum pressure amplitude, I think we also have to find the answer to part B, which is the displacement amplitude of the wave in the fluid of the inner ear. So something is going to be gotten in another way because there's two different things that are unknown here. We can obviously look this one up, that's not a problem. But these two are connected to each other, so there has to be an alternative way to find one of them. It's probably going to be pressure, because that's the part they ask first. It doesn't have to be. But once we find the pressure, we can use this K to find what the amplitude needs to be. It's going to have to be related to these two quantities here. It just isn't immediately obvious to me how it is. So if the maximum pressure variations out here in the air, right, are, what was it, 3 times 10 to the negative 2 pascals, and they enter your auditory canal, which is also made of air, and then this piece is connected to this. The question is, within this region here, which has a smaller cross-sectional area, what are the pressure variations are going to be? I don't know how to do this. Does anyone know how to do this? I have to actually look it up. I don't really understand what I need to do. I've been resisting doing this. I hate doing this. Usually I can just figure these problems out, but I can't for this one for some reason. I want to read what they say, because I have to. I don't really understand what's going on. It says, although the second wave here travels in liquid rather than air, the same principles and relationships among properties of the wave apply. We can ignore the mass of the tiny ossicles. I don't know how you're supposed to know you could do that. Apparently they weigh 58 milligrams. So the force they exert on the inner ear fluid is the same as that exerted on the eardrum and the ossicles by the incident sound wave. This is like saying that the tension is the same at either end of a massless rope. Hence the pressure amplitude in the inner ear, P max inner ear, is greater than in the outside air because the same force is exerted on the smaller area, the area of the stapes, versus the area of the eardrum. So their claim is that P max should be related to some force over area. I'll use area to be clear that this A is different than this. And that the force can be gotten, so force is pressure times area, right? So this would be pressure in the air, maximum, times the area of this, which is the area of the drum, I think, divided by the area of the stapes. Does that make any sense at all? Yeah. There's a lot going on. Exactly, Matthew. All right, let's read it again. I mean, I think I got the formula I got right for sure, but the question is, why is that the formula? So the claim is that the ossicles. It says, we can ignore the mass of the ossicles. The force they exert on the inner ear fluid is the same as that exerted on the eardrum and the ossicles by the incident sound wave. Hence, the pressure amplitude on the inner ear is greater than on the outside ear because the same force is exerted on a smaller area. Okay, so a force comes in here in this direction, right? That's where the force is coming in. It affects the canal here, but because this canal is connected to this much tinier piece right here that has a smaller cross-sectional area, just like a thumbtack, the pressure on this side is going to be larger than the pressure on this side because it'll be the same force transmitted throughout the entire thing. I guess the way that I'm thinking about that is that if this is the ear, then the canal that connects it makes it go down to a very, very tiny point like this. So we have the area of the drum over here. And then we have the stapes or the stirrup over here, which has a smaller area. And when you apply a force in this direction, F, you get a pressure of F times A, but the pressure over here is going to be greater by exactly this amount. That's kind of what they're saying. I feel like that's an awful lot to put into an example problem, but I think kind of the point of this example problem is to kind of have some kind of connection between anatomy and what we're discussing. Anyway, so given that that's how we're going to do it, all we have to do is we just need to take the max air pressure that we got in the previous problem of 3 times 10 to the negative 2 pascals, multiplied by the area of the drum, which was 43, divided by the area of the stapes, which is 3.2. Both of these are in mm squared. So that will cancel. So if we do 43 over 3.2 times 3, we're going to get 0.4 pascals. That's going to be our pressure on the inside. Call it maybe pressure inner. And then we can use this along with this equation up here. We have to look up the bulk modulus of water. I'm assuming they're probably just going to give it to me in the problem. So it's 2.18 times 10 to the 9. So B water is 2.18 times 10 to the 9 pascals. And then we just put those all together with our equation here. We're solving for the amplitude, A. So we're going to have, sorry, this is kind of going all over the place. A equal to P max, which in this case is going to be P inner, that we just calculated, divided by KB. So it's going to be 0.4 pascals divided by K that we calculated here. And then multiply by bulk modulus. Still on the screen, which is good. We calculate this, we're going to get 4.4 times 10 to the minus 7. Did I do something wrong? Oh, whoops. Yes, I did. So it's divided by 4. So minus 7 goes to minus 11. 4.4 times 10 to the minus 11. That's what I get on this one. And what does that represent? That's the displacement amplitude, which means that the particles within your ear, the water particles, they're vibrating back and forth with this kind of an amplitude of 4.4 times 10 to the minus 8. So that's how much they're vibrating. That's a very, 4.4 times 10 to the minus 11, very tiny number. This is on the order of the size of an atom, actually. That's how little variation that's occurring inside of these things. Okay. Any questions? So you're saying you can hear from 2 hertz up to 2,000 hertz. I don't remember off the top of my head what the actual range of what we can hear is, but I thought the range of frequencies we could hear was something like 1,000 up to 20,000. Maybe I'm wrong though. Where did you get the 2 to 2,000? Maybe you're right. I don't remember. It's definitely something that they talk about at some later point in this chapter, but I just don't remember what the numbers themselves are. From 2 to 2,000 is what they said? It depends. Do you know where it was? Just make sure. They're saying that the pressure of the inner ear times the area of the stakes equals... Yes, that's right, Astrolover. That's right. That number... Okay. Where do they talk about that? About the... So there's this thing called the threshold of pain, which is like the highest frequency sound we can hear without feeling pain. Or is that for the intensity? I don't see it immediately in the textbook. So maybe they do talk about it, but... Oh, no. Wait. No, that's not it. Okay, yeah. 20 to 20,000. Isn't that what I said? I said 20,000 was the kind of maximum range. Yeah, okay. All right. Anyway, so next thing we want to talk about, wondering again the assumption of 1,000. So let me go back to your original question. It's just a particular value given in the problem, Troy. There's nothing special about it. I do know that this 1,000 hertz is used as like a reference frequency for the decibel scale, but this is it's just given as 1,000. It's not. There's nothing special about it. You know what I mean? I wouldn't read too much into it. Okay, so next thing we want to talk about is the kind of, we're talking about sound, right? So what do we actually hear? So I'm talking about perception of sound waves. So in physics, we can talk about things like frequency, velocity, wavelength, pressure, amplitude, all these things. But the question is, what do you actually hear? When we hear sound, we hear something that we describe as how loud it is, right? Loudness. You can crank up the volume on your stereo or your TV or your phone or whatever, and we can increase the volume of sound, right? Loudness of the sound. Well, the loudness, the amount that we hear, is directly related to that maximum pressure amplitude that we were describing, which then is again related to the displacement amplitude, like what we calculated right here. So, just going back to this previous problem here, this quantity here, the kind of change above and below atmospheric pressure, the bigger that this number gets, the bigger the loudness gets, right? We also have something called pitch. I've been using this word quite a bit, but pitch corresponds to frequency. And then the other thing to understand is that I guess kind of like not all sound waves are going to be as simple as the ones we've described. So shown here are 2 different sound waves. one that's being produced by a clarinet, and then C and D, these are produced by an alto recorder. A recorder is just something that's similar to a clarinet but produces a different kind of sound. So the sound coming out of the clarinet, here, this is what they're showing down here at the bottom, is the pressure fluctuation versus time for a clarinet with a fundamental frequency of 233 hertz. And what you end up seeing is that the waveform, while it's periodic, right, this waveform is repeating itself, right? So where does the wave repeat? Basically, if we start from this point right here, the wave goes down to the bottom, and then it does this thing, and then it does that thing, and it comes back to here, and then it goes through and it repeats that exact pattern again, eventually coming back to the same point. So it still has the properties of being a wave, but it's no longer a simple sinusoidal wave, right? If we compare that to the pressure fluctuation, now again, this is pressure versus time that's being plotted here, right? This is the pressure fluctuation versus time for an alto recorder with a fundamental frequency of 523 hertz. So the frequencies are different, but the recorder here seems to be producing a very sinusoidal wave function, right? And that means that when you hear a tone produced by the clarinet versus a tone produced by a recorder, they're going to sound different from each other. The clarinet is almost going to sound, I don't know what the right way to put it is, but fuller, because the frequencies that are being produced by the clarinet are much more complex than those being produced by the recorder. And the way we could see that is by doing something that's called Furrier Analysis. Wait a minute. Can you all even see this thing in the bottom left? Oh, maybe you can see most of it. Let me see real quick here. Okay, you can see it now. That's good. They do this thing called Furrier Analysis. Is this something you all have talked about in your math classes before? Furrier Analysis? I don't know if you have or not. So Furrier Analysis is a method by which you can, I'll write the word down in case you don't understand what I'm saying. Because it could have been, you don't think it's come up. So Fourier Analysis, I think it's Fourier, I don't really know, is a process by which you take a complex wave and you decompose it into kind of like sine and cosine waves, effectively. And that's what's been done going from this picture down to this picture here, okay? This wave has been Fourier analyzed. There are programs that can do this for you. Probably at some point in time, you're going to take a math class where you learn how to do it. But what happens is you take this complex wave and you break it down into a bunch of different waves, a sum of waves that all have different frequencies, okay? And so notice what's being said down here at the bottom. So this is now plotting, instead of pressure versus time, you go into a new space where you plot the amplitude versus frequency, okay? And in this case, this is going to be the amplitude of, the loudest sound is going to be the one that has the biggest peak here. The one that stands out to you, okay? And it's kind of hard to see from this thing right here, but what's being plotted on the bottom is different fundamental frequencies, right? So F1 was 233, right? So this right here is 233 hertz. Right here, that's F1, right? But you also have, looks like 3 times F1, 5 times F1, some 6, 7, 8, and 9 times F1. This is why, so the playing of the clarinet, it doesn't just produce just this one note. Remember that a frequency directly corresponds to a note. It also produces all these higher notes as well. They are higher for sure, right? Because higher frequency is going to be higher pitch, right? And as a result, the music produced by the clarinet is going to sound kind of a lot fuller. It's going to have more timbre, what they say, than this over here. Where, if you notice that this one, when you Fourier analyze this one, you just mostly get the biggest peak that occurs here is right at F1, and maybe another peak right here, that first overtone, F2, but it's really just those two notes, okay, that you're hearing there. It's almost like an example of this would be, I wonder if I can find something to do this on the internet real quick here. So what we need is like an electronic keyboard. Now this is going to be one where it's produced by, what do I need? Online. Virtual piano. Okay, this should work. I don't know if I can do this because I only have one mouse clicker. But when you play like a... Oh, I can, because I can do stuff like that. Wow, it actually sounds like a real piano. Can you all hear that? You can't, can you? We're going to have to switch screens. Change windows. Virtual piano. Go live. Okay, that doesn't kick you, right? Yeah, you're still on the stream. Okay, so so this button is middle C, I think. And when we play this, you get a sound. That actually sounds like a real piano, so probably the sound that's being produced here is actually probably closer to being like a bunch of overtones too. So what can we do? What are the buttons I need to push here? So this button, if we push that, it produces a sound. Can you all hear that now? Is it loud enough to where it's audible? Okay. So if we go, so this key is called C, right? But this key right here is also called C. And if you play this one, and then you play this one, I don't know, do they sound like the same note to you? It's different frequency, like this is higher than this one. But the question is, does it sound like the same note? What's a note? It sounds one octave higher. That's what it's supposed to sound like. That's right. There's this one, and then this one. And when he says one octave higher, the idea of that is that I could play an entire song starting from this key and just using these keys, or I could start from this key and play using these keys, and I could still, it would sound the same, but it would just be higher pitch. The song would still sound the same. That's the way I think about it, right? Okay, so, but look what happens if I push both at the same time. So if I push this one and this one at the same time, I think this will work. I don't know what that sounds like on your speakers or your headset or whatever, but it just sounds like you made the sound richer in a way to me. Like this sound and this sound had a certain sound, but when you play them together, you're effectively getting both of those frequencies at the same time. And they are related to each other by a whole number multiple, right? I don't know exactly what the multiples are, but if this one is, let's say that this one right here is 256, this one's going to be 512. It's going to be double. So when you go from this one to this one, it's doubling the frequency. But what that means is if you have two waveforms that have a frequency that's a whole number multiple of each other, then when you play them at the same time, they won't interfere with each other, right? And what do I mean by interfere? Well, if I play two keys that are right next to each other, so let's see here, if I play this one, and then this one, you can audibly tell that that's a different note, right? That this one and this one, they sound completely different, right? If I play them at the same time, though, those of you that have ever done this on a piano know exactly what this is going to sound like. It'll sound horrible, right? That's what we call dissonance in music. Because you have two waveforms that have frequencies that are really close to each other. And when they play together, it just sounds bad, right? Would you all agree it sounds bad? Does this sound good to some people? I don't know. It sounds like they collide. That's actually exactly what's happening. It's because you've got one wave and another wave, and their frequencies are really close to each other, and so they can't like harmonize with each other. They can't find consonants. But when you have two waves like this one and this one, you can barely tell that's two different piano keys, right? It just sounds like those are two different keys because you can tell the pitch is different. But when you play them both at the same time, like it almost sounds like that's the same note, right? Okay, so let's take this back to what we were just describing. I will say, by the way, you don't have to have two notes that are exactly 8 keys apart to get consonants. You can also get consonants if they're 2 keys apart. You can get a ton of consonants if you play 3 in a row that are 2 keys apart, like that, which is what a chord is. Actually, I don't think what I played was a chord, but regardless. So now let's go back to here. Let me change the screen to change windows to OBS. So when you play a clarinet, right? Here, you're getting all of these different frequencies. So this, when you play the clarinet, it's like hitting 1, 2, 3, 4, 5, 6, let's say. These ones are really small. It's like hitting 6 of those keys at the same time that are all exactly 1 octave apart from each other. That's what this is telling us here at the bottom. It's telling us that the clarinet produces this really complex waveform, but when we analyze it, it's really just a bunch of different waveforms that have very similar frequencies to each other, that are all whole number multiples of each other. That's why it says on the bottom 5F, 10F, 20F, etc., is because it's always whole number multiples of that original frequency. Okay, so that's like trying to get at the difference in the kind of things that we hear and how it's connected to music and stuff like that. Loudness is related to pressure max, pitch is related to frequency, and then any given wave that we have, we can decompose into these other little waves here. And you can find all sorts of tools on the internet to do that. In fact, I'm pretty sure on this website there's a way to do it. I know on a lot of laptops and stuff like that, you can have, let's see, does it have, yeah, Furrier making waves right here. So we may use this next time, but because I think it has sound involved in it as well. Anyway, let's keep going. What time do we get out? Do we get out at 11:50 in this class? I think we're kind of pushing up against the edge, right? All right, well, in that case, let me see if there's anything else that I really wanted to cover today. I definitely wanted to cover this, but I have these other problems over here related to the speed of sound. I think we can do at least one of them. So let's talk about speed of sound real quick. So speed of sound. Now, when we talked about the speed of a wave before, what we said was that the velocity is going to be related to something like the square root of some type of a force thing, some kind of a restoring force. So in the case of our rope, it was tension, divided by something related to inertia. In the case of our rope, it was mass per unit length, right? So tension over mass per unit length was an example of this, right? But when you have a sound that is in a fluid, now that we know some things about fluids, the restoring force is going to be how bendy the medium is, how flexible it is, which is going to be bulk modulus B. And the inertia force is just going to be the density of the fluid itself. So in a fluid, this is going to be our velocity. So if we plug in the bulk modulus of air and we plug in the density of air, we could do that real quick, right? Because didn't we have from above what the bulk modulus of air was? It was like 10 to the 5. It was from this problem, right? Yeah, 1.42 times 10 to the 5 pascals. Let's see if this works. So if we do 1.42 times 10 to the 5 pascals for the bulk modulus, and then what's density of air? Density of air is it like 1 gram per meter cubed? Is that right? Which would be 1 times 10 to the minus 3 gram per meter cubed. Does that sound right to you all? Kilograms, sorry. Maybe we should go look it up. I don't know if that's right or not. I think that's close to right, though. .225 times the kilogram. Oh, it's 1 kilogram per meter cubed. 1.225 kilogram per meter cubed. Okay. I was thinking 1 gram per meter cubed, but it's 1 kilogram. It's 1.23, we'll say. What's that if we do that? I can see how that's going to work out. It looks like it's going to work. 1.42 E5 divided by 1.23 to the 0.5 power. Yeah, you get 340. It's not exactly the same number, but it's pretty close. And I'm sure if I used more digits on these things, it would be even better. So you get about 340 meters per second. So that's pretty close, right? The other possibility is if you have a solid. In a solid, we have to replace the buoyant force with the Young's modulus y that I alluded to earlier. And then we have to divide by also density, right? Okay, so that's going to be the velocity in a solid. And then I think we can use, we can solve a couple problems with this that we have on here. Where are they? This one. Cut. We'll Let's do at least one of these. Okay, so here's some examples of the values of the sound in various materials. You can kind of look at this and talk about it. So in gases, we got the speed of sound in air, helium, and hydrogen. Helium has a higher speed, probably because the bulk modulus is maybe bigger, but definitely the density of helium will be lower than the density of air. Hydrogen will have the least density, so the speed of sound in hydrogen is going to be really high. I believe that this is a direct connection between why it is that when you inhale helium and from a balloon or something, and then you try to talk, that it sounds really high frequency, right? Because frequency is equal to wavelength divided by velocity. Wait, that's not right. V equal to lambda f. Frequency is velocity divided by wavelength. So if you're talking through helium gas, then the frequency that you produce is almost 3 times as big, right? Not quite, but close to 3 times as big, which means the frequency is going to be about 3 times. And that's why it is that when you talk with helium in your lungs, that it sounds really high frequency. Then we've also got the velocity, the speed of sound in liquids. You've got water at 3 different temperatures here. It's about 1400. And then down here in solid, you can see that the speed of sound is really high. It's really high in all of these things here. Probably because they are not very stretchy. So the Young's modulus, I believe, is on the order of 10 to the 10, whereas the densities are on the order of 10 to the 3. And so as a result, you get really high speeds in solids. And of course, that's because the solids are just more densely packed too. All right, so here are some examples. The first one is a really short example. So it says, a ship uses a sonar system to locate underwater objects. Find the speed of sound waves in water using the equation 16.7, and find the wavelength of a 262 hertz wave. I also included here what the bulk modulus is. So all we have to do is just say V is equal to square root of bulk modulus divided by density. We're in water. So the bulk modulus, as I said, is given right here, 2.18 times 10 to the 9 pascals. And then we just divide by the density of water, which we know to be 1,000. And we just square root it. We're going to do this on one other problem. I know we're out of time, but we did start kind of late. So this divided by 1,000. And then we raise that to the 0.5 power. I got 1476 meters per second. And then we want to find the wavelength of a 262 hertz wave. So lambda is going to be equal to V equal lambda f. So lambda is equal to V over f. So that's going to be the velocity we just got, 1476. Then we divide by frequency, which is 262. So dividing by that, that's hertz. Our wavelength lambda is going to be equal to 5.6 meters. It's a long wavelength, 5.6 meters. All right, we're going to do one more problem because this one is a little more interesting. So this one's also related to some stuff that we have been... Oh, there's that range you were talking about, Troy, right there. So one final thing here, which is that we can talk about the velocity of sound in air. And for this one, we could probably derive this if we wanted to because we have all the math behind it, but for some reason they just don't. So we get the square root of gamma RT over molar mass. So gamma, what's gamma again? Gamma is the ratio of heat capacities. Something you're all pretty familiar with a lot of the problems we've been doing. They showed up a lot in the last exam. M, molar mass, we know what that is. Also write down that it's molar mass. And T, obviously temperature, absolute temperature, and then R is the gas constant. Sorry, this should be the velocity of sound in a gas. There we go. All right. Apparently, for a gas, the bulk modulus is related to gamma and related to the kind of absolute pressure P naught. Anyway, not super important. Interesting thing about this is, just order-wise, we're in chapter 16 right now, and I think gamma is introduced in chapter 19 or something like that. So it's interesting that just the order of the textbook that they even put this in here, because you wouldn't have learned about gamma yet. Regardless, here we go. Find the speed of sound in air at 20 degrees Celsius, and find the range of wavelengths in air to which the human ear, which can hear frequencies in the range of 20 to 20,000 hertz, is sensitive. The mean molar mass for air is this and this. Okay. Very plug-and-chuggy equation. We're going to have V equal to gamma, which is 1.4, multiplied by R, which is 8.31 joules per mole Kelvin, multiplied by 20 degrees Celsius, but we got to convert that up. So it's going to be 293 Kelvin. Just add 273. Divide by molar mass, which is given as 28.8 times 10 to the minus 3 kg over mole. Square root that. Velocity equals. Well, I did something wrong. What did I do wrong? Oh. There we go. All right, end up getting 344. Not too surprising. Find the range of wavelengths that we can, okay. So wavelength is going to be velocity divided by frequency. So for the low end, we're going to have 344 over 20. And then for the high end, we're going to have 344 over 20,000. So divide by 20, 17. And then this one's going to be, what's that, meters? And then if we multiply by 20 and divide by 20,000, we get 0.017 meters. Okay, that's where we're going to stop today. Next time we will finish up with this chapter, discussing sound intensity, decibels, and I guess we'll talk about resonance, interference, waves, beats, Doppler effect. Mostly what we're going to focus on is the Doppler effect, the decibel scale and intensity, as well as, I guess we'll do one of these interference problems. Oh, and we'll talk about wind instruments. All right, so that's all for today. Hope you all have a great week. I'll see some of you on Wednesday, and I will try. I guess at the very least, I'll give all your exams back during that class. So, how are you going to get your exam back if you're not actually showing up on Wednesday? That's tricky. Maybe what I could say is, if you do show up on Wednesday, anytime from, so the first class starts at 9:45 and I get out at uploading the exams on Canvas. Whew, man, the ways in which I don't want to do that. Maybe the only option though. I'm not required to return your exams. Yeah, I could definitely give them back on the day of the final, Richard. Absolutely. The problem is you can't see what you did wrong then. Well, before the final, right? That's the problem. So, I think you're just going to have to come into campus if you want to get them. If you really want to see the grade, I guess, the thing is I don't really have a scanner at my house. I guess I could take pictures. Whew, that's a lot of tests to... just come in Wednesday. But don't come in right at the beginning because I might not be finished grading. If you're there for the lab, I'll give it back to you for sure. But if you come in at the end of class on Wednesday, so when class normally ends, I'll have all the exams graded by then for sure. So, yeah. Come in Wednesday if you want to get your exam. You don't have to come in during the class time. I'll be on campus from 9:45 until 4:30, 4:20. I think is when I get out. So if you want to come get your exam, show up from about, let's say, 1 o'clock. I mean, from about 12:45 to about 4:20 p.m. From those hours, you should be able to get your exam back if you really want it. Okay. Okay, that's all for today. Did I already stop recording? No, that's good because it's good.